Hi guys, Dr. J here, and in this video we're going to continue talking about gravity potentials and how they behave, and we're going to talk specifically in this video about potential of mass, different distributions of mass. And what we're going to do is we're going to start by just reminding ourselves about what we talked about last time, which is that the gravity field or the gravity acceleration is the negative gradient of the gravity potential. And again, sometimes it's negative gradient, sometimes it's positive gradient. And of course, what do we have about the gravity field? We have that the gravity field is equal to negative g mass over distance squared times r hat. So there's our vector, our unit vector. So we have gravity field and gravity potential are related this way. This is kind of from what we talked about last time. So now we're going to think more specifically about the potential as a function of mass and distributions of mass. And we might want to be able to figure out, of course, the potential of the Earth, but we might also be interested in other kinds of mass distributions, or maybe we're interested in missing mass from the Earth. Maybe we're trying to find a cave or a mine using gravity, for example. So let's talk about the gravity potential in general. So here again is our gravity potential. So gravity obeys Laplace's equation outside of any mass sources. So we've talked about this before. Del squared U is equal to 0 if we're outside of all distributions of mass, outside of all sources of mass. Okay, so that's Laplace's equation, and the gravity potential obeys that. Because of that, this governing equation, again, this is outside distribution of mass. We won't worry about inside for the moment. But because it obeys this equation is what's called a linear equation, and that means that it obeys the principle of superposition. Superposition says that if you have, I'm just going to write a bunch of little boxes here, and if you have a bunch of little boxes with each having their own density, density 1, density 2, or I should probably say mass 1, mass 2, mass 3, mass 4, it's the same thing if the boxes are all the same volume. So they each have their own mass. If you have some observation point out here, we'll call that P. That's just where we're measuring gravity. The gravity that you measure at this point is the sum of the gravity from this one, the gravity from this one, and this one. They all simply add up. And not all equations, not all kind of physics relationships behave this way. They don't always add up like this so simply. But in this case, gravity does, and that's good news for us, because that allows us to do some very nice things. And one of the things that it allows us to do is to say that the potential, we've talked about this in another video, the potential, gravity potential, is the sum of a lot of little masses divided by the distance to those masses, and we're just going to sum it up from I equals 1 to n. So this is very easy, very simple. The gravity potential from a collection of masses is just the sum of all those masses. Now, what happens in the limit as the little masses, and I really should say here, I can say this in another way. Instead of saying mass, I can say a volume and a density. Okay, so the volume times the density gives us a mass. So now I have, again, this goes back to my example that I just erased, and I'll put back on the board now. Sorry, not very good at drawing. But I have a bunch of little boxes. Each one has some density, and I can take the volume of that box times its density. That gives me the mass of the box. So mass I is equal to rho I VI. And the I here just means the ith box. So I'm taking the ith unit out of all my different little masses. So this would be mass 1 is equal to density in the one box times the volume of the one box. Mass 2, mass 3, mass 4, mass 5, so on and so forth. So this would be, I could just say 1 here for this box, okay? So it's just the sum. We can get the total potential by summing up the masses of all the boxes. That's the same thing as summing up the density times the volume of each one of the boxes, okay? Hopefully that makes sense. Now what happens in the limit as the volume goes to 0? Let's say we have an area, a large area, and I divide it up into a bunch of little boxes, and I calculate the volume and the mass, or excuse me, the volume and the density for each one of the boxes, and I multiply those together and get the mass of each box, and I add those up. That's fine. But now what if I take the limit as these things get smaller and smaller? And for this example, let's just assume we have a constant mass, a constant density here. So all the densities are the same. So those will pull out of the summation. We would just have density times the volume of each box divided by the distance. Here's again our observation point P over here. And so we're summing up all these things, and we make these boxes smaller and smaller and smaller. You can see what's going to happen. We're going to get a continuous distribution of mass, and we're going to represent that with an integral. So now instead of having a sum, we'll have an integral. But this even works without having a constant density. It can be any density. So what we can do now is we can say this is equal to the integral. Oh, and I've missed one thing here, which is the gravity constant. Gravity constant is there. It's a constant. We don't have to put it inside the summation or the integral. So gravity constant is here. And then I've got the integral of dm over r, which is equal to g times the integral of the density divided by r dvq. So what have I done here? Same thing as I was doing up here. We have the integral of the density in a bunch of little boxes, little small units of density, just adding them up, but we're doing it in the integral form, so it's continuous. Here I've pulled out the density, and I've got the volume here. And Q here is just an integration variable. So if you remember back from calculus, this gets integrated over. So we could just say, I could get rid of the Q actually. Maybe that's simpler. It's just the integral of density over distance times the volume increment. We're integrating over the volume. There'd be some total volume that we're integrating over. And we're going to integrate the density divided by the distance to each individual little tiny point inside that volume and integrate over the whole volume. Okay, so this is how we can write it. Again, these might be changing in space. So rho could be a function of x, y, and z, and that's why I had that point Q in there. So Q is just the point where the mass is. So what have we done? We've set ourselves up so that now we can calculate for any density distribution and for any arbitrary volume, we can simply integrate the density over that volume to calculate our potential, right? So we are able to do that now. This still satisfies Laplace's equation outside of mass sources. So if we have some density distribution and we're outside the sources of all density, if our observation point P, so I should say this is now going to be, so P is always going to be our observation point. Q is going to be the point where the mass is. So we had dV of Q, density at location Q. So our mass is at Q, our observation is at point P. We're going to integrate over all the masses that we have. So this outside of those locations where Q is, so in other words, outside of all the mass, the potential here, we can do the math. The book does it. We can see that it obeys Laplace's equation. It obeys our gravity field is equal to the gradient of the potential. Another form for the potential is given by equation 3.8 in your book, and that is 1 over 4 pi integral del dot g. G here is our gravity acceleration over r dv. So we can basically do a substitution, and that substitution is based on the Helmholtz theorem, which we talked about in the last module. And remember that g here is a vector, so we're taking del dot a vector. So this is our divergence of the gravity field. And if we compare equation 3.8 in the textbook with equation 3.5, we get the following. Del squared u, remember del squared is our Laplacian operator, Laplacian of the potential. And the Laplacian of the potential we set up here was equal to 0 if we're outside of the sources of mass. So here we're inside the mass, or maybe we are inside or outside. And we can actually see this is going to be negative 4 pi g So this now is just a different form of this equation. So this is the integral form. This is the differential form. This is Laplace's equation. It says that the Laplacian of the gravity potential u is equal to negative 4 pi times the gravity constant times the density at that particular point P. So this is the Laplacian u at the point P. And this is Poisson's equation. So this comes about because where the density is equal to 0, that's where we're outside sources of mass. If the density is equal to 0, this is Laplace's equation. And we've already seen that. We know gravity obeys Laplace's equation. That all is good. What happens if we're inside the Earth, for example? What's the gravity potential then? Well, we have some density, so we can't say it's Laplace's equation because this is not equal to 0. But this here gives the formulation in terms of the density at that location. And this is called Poisson's equation. So Poisson's equation is like Laplace's equation when you have a source term in the partial differential equation. So that is Poisson's equation there.